Welcome students. Today, we want to discuss about some primitive factorization methods. And this will justify to some extent that factorization is indeed hard, and hence our RSA is in some sense robust. So one of the factorization method we all know is the following, which is called trial division method. The idea here is list the primes P which are less than equal to n and check if n is divisible by one of these primes. If yes, you get a factorization. If not, we have that n is prime. Recall we had a theorem saying that one of the factors will be less than equal to square root of n. So one of the, okay. So second method is called Firma's factorization method. Again, you want to basically factorize n, an odd integer. So the idea is, nutshell, the idea is that you want to write n equals to x square minus y square, which will give me x minus y times x plus y. So this is the idea behind it. Okay. So how do we go about it? So what is an algorithm here? So your n is equal to AB. Yeah, you do not know these ABs, right? So, and n is odd. So let T be ceiling of square root of n. Then we look for squares. Look for squares in T square in T square minus n T plus 1 square minus n dot dot dot. You go all the way until n plus 1 square minus n. Yeah, and at this point we stop, all right, because this is already going to be n minus 1 by 2 square, and which will give you a trivial factorization. We'll see that. So now note that if t minus t plus I square minus n is a square is equal to y square, then we already get our factorization. Then this implies n equals to t plus I square minus y square. Call this as an x. So we get this is x square minus y square. So this is going to be x minus y times x plus y. Yeah, and we hope that these, so hoping that this factorization is non-trivial. Non-trivial. In fact, we have to see when is the factorization trivial, right? So In fact, we make a following claim. So claim there is one-to-one bijection. So let's say n equals to AB with 1. So we are assuming that n is not a square. So there's one-to-one correspondence between this guy and x minus n equals to y square, where your 1 is less than y less than x, and we have that your t is between, your x is between t and n plus 1 by 2, right? So let's see the correspondence now. Note that if t equals to n plus 1 divided by 2, in that case we'll get n plus 1 by 2 square minus n equals to n plus 1, n minus 1 divided by 2 square. This is an identity you can clearly check, or you get n equals to n plus 1 by 2 square minus n minus 1 by 2 square. In that case, you get basically n plus 1. So when you add this, you'll get n plus n minus, so you get 2n by 2, and then you get 2 by 2, which gives me n, and that means n times 1 equals to n. So the idea is that if t is here, if you choose x to be n plus 1 by 2, then the problem is, so not t, my bad. If your x is n plus 1 by 2, then you get basically trivial factorization of n, okay? So this is the idea. All right, so now we want to basically claim there is one-to-one correspondence, one-to-one correspondence between set collection of objects here from 1 to 2, which are solutions to this x square minus n equals to y square. Okay, so let's establish this. So if, say, if n equals to AB, then, and with following, consider the following math. We have x equals to a plus b divided by 2, and y equals to b minus a divided by 2. Yeah, so note that since n is odd, a b implies a and b are odd, and this implies a plus b by 2 and b minus a by 2 are integers. So given the factorization for n here, we are producing a solution x and y such that x square minus n equals to y square. That you can check really. So if my x was this, I can clearly show that my y is going to be y is going to be b minus a by 2. That can be shown by the following. So we have a plus b by 2 square minus n, which is ab, is going to be a plus b square minus 2ab divided by 2, and you can see that this is going to be a minus b square divided by 2, but we'll choose b minus a by 2 because that's the same value. So why is that? Because b is greater than a and we want positive integers. So therefore we choose, so y is going to be b minus a by 2. So the map is given factorization. So given factorization, we are producing a and b, which satisfy the following. Now we have to show that it indeed satisfies that. And how are we going to show that? So we need to show two things. We need to show that t, so 1 is less than equal to y is less than x, and also that t is less than equal to x less than equal to n plus 1 by 2. So we want to show that these two are also true. So clearly, uh, the first part is clear. Why? Because b minus a by 2 is greater than equal to 0, right? It's an integer, right? So therefore, it belongs to z plus, right? So therefore, therefore, y must be greater than equal to 1. And clearly y is less than x because the way y and x are defined, right? So you can think about it as b plus a by 2, and then you can clearly see that this happens. Now the second part is more interesting, which is namely, sorry, the second part is more interesting, namely that t, so now we need to show that t is less than equal to x less than equal to n plus 1 by 2. So now clearly, note that t, so t is, so how do I show that? I'll show it here. Note that a plus ab is less than equal to a plus b by 2. Yeah, this is the arithmetic geometric mean for all real numbers, in fact. But so this is your, so this is true, and this is an integer. Therefore, ceiling of this guy, right? So ceiling of this guy is also going to be less than equal to a plus b by 2, which is your t. So therefore we get t is less than equal to x. Now we want to show that x is less than equal to n plus 1 divided by 2. Now part 2, so to show that x is less than equal to n plus 1 by 2 is to same as showing x a plus b, x is a plus b, so a plus b divided by 2 is less than equal to a b plus 1 divided by 2, which is same as saying a plus b, so ab plus 1 minus a minus b is greater than equal to 0. That is same as basically saying, that is same as to show that a b minus a minus b. So you can see that this is same as a minus 1 times b minus 1 uh, plus 1 is greater than equal to 0, right? So which is indeed true, right? So therefore we get x is less than equal to n plus 1 by 2 less than greater than equal to t. So what have we shown? What was all this discussion about? So we want to produce one-to-one bijection between n equals to ab, the factorization of it, and the solution to x squared minus n equals to y squared. The reason for doing that is, I mean, one may argue, well, you may have a factorization here in a, or as n equals to ab, which may not show up in this kind of solution finding or finding for x and y, but that is not true, because now we have shown if there is a factorization n equals to ab, you will get x and y which satisfy this. Okay, so conversely, so you can think about conversely now, x and y, let conversely, if x and y satisfy star, which is basically, let me write down here, satisfy star, you can produce a factorization for n, namely as n equals to x minus y times x plus y. Yeah, why is that? Because, well, your xy satisfies x square minus n equals to y square, that is n equals to x square minus y square, right? And which is basically this part here. So what is the point of this discussion? So the point of this discussion is the following. If you are using the Fermat's factorization method for n odd, and particularly if n is square free, if it is square free, then we can still work it out. But if it is square free, that means it's not, a is not equal to b, then we get one-to-one correspondence. We have shown one-to-one correspondence between the factors a and b and x and y such that x square minus n equals to y square. So this works indeed, all right? Okay, so no factors, it's not that you run this process and a factor, you won't be able to get a factorization. If the factorization exists, it will show up. All right, so let's look at an example now. The factorization of 143. So suppose this is your n. Yeah. So if you look at ceiling of n, square root of n, this is your t, right? So t is square root of n and then take ceiling of it. So you can see that it's roughly around 144. So ceiling of this is going to be 12. So you start with 12 plus 1. So 12 plus 1 and then look for basically, so you're looking at 12 square minus 143 and see if it is square or not. Well, you get in this case 12 square minus 43 is 1. So, well, this is the easiest one in some sense. So we get 143 equals to 12 square minus 1 square, which is 12 plus 1 times 12 minus 1, which is 13 times 11. All right, so this one was pretty straightforward. Let's look for another one. So namely, let's take 2 n equals to, so let's take n equals to 2 to 1. All right, so now what is the, so t, which is going to be square root of 2 to 1 and then ceiling of that. So let's see what is this, what number is near 2 to 1 and is the square root. So this is basically same as square root of 2 to 1. So you see the nearest square is 15. So this is going to be 15. So then we get, let's look at 15 plus 1, sorry, 15 square. So you look at t square, t plus t square minus n, right? And then, sorry, t square, t plus 1 square minus n and so on, right? So let's see, 15 minus square minus 2 to 1, and that is going to be already 4, which is 2 square. Oh, too bad, my examples are too easy, it seems. So this gives me 2 to 1 equals to 15 square minus 2 square, which is going to be 15 plus 2 times 15 minus 2, which is going to be 17 times 13. Note that Firma, so this may give us a bad impression that Firma's factorization is very effective. Actually, it is not that effective, and depends on how the factors are distributed, right? Let me take another example. Say n equals to 6, 6, 7. So what is the ceiling of this? So ceiling of square root of 667. So recall 625 is the square of 25, right? So 667 ceiling will be 26. So this is going to be 26. So now again, we'll do the following. We'll check n, we'll check for t square minus n, t plus 1 square minus n, and so on until we get a square. So what is t square? So 26 square minus n. So basically 26 square is 26 square is basically 676. So we have, this is going to be 676 minus 667, which is again going to be 3 and 3. Oh, okay, 9. Huh, all right. So we get, this is going to be 4 here. Sorry, my bad. So this is 676 minus 667. So 6 extra and 3 there. That's right. So it's 9, already 3 square. So therefore we get n equals to 26 square minus 3 square, which is 26 plus 3 times 26 minus 3, which is 29 times 23. All right, so now we need some, well, these examples are in the sense somewhat, I have chosen this example randomly and it turns out, but this is not the case. So let me take another example. So for example, let me take 10003. So in this case, what do I get? I have ceiling of 1003, square root is t. Now note that 1003 square root is like root 10 times root 100 roughly, right? So and then I'll add 1 to it. So root 10, so this is going to be roughly 32. So t is equal to, so ceiling is basically 32. So now what you do is 32 square minus 1003 and check what do we get. We get 21. That's not a square. Then we need to see 33 square minus 1003 and see what is that equal to. So that is equal to so let me square it. So we get 86. That is also not there. What about 34 square? 34 square minus 1003 is going to be 34 is 153. That is also not a square. What about 35 square minus 1003? So we get 35 square minus 1003 is going to be is 2, 2, 2, which is also not the case. What about 36 square? 36 square minus 1003 is, so these are not the possibilities, right? So 36 square minus 1003 is going to be uh, 36 is going to be 293. So that will also not work. And then we get 37 square minus 1003 is 366. That will also not work. I'm using the calculator now. All right. Whereas 38 square minus 1003 is going to be 441. And that you can already see is basically 21 square. So what do we get out of this? So we get 38 square minus 103 is 21 square. So in this case, we get 1003 equals to 38 square minus 21 square, which is going to be 38 minus 21, 38 plus 21, which is going to be, so you get 2, so 17 times 59. So this is a factorization of 1003 using Fermat's factorization. So you see that this is really a long method. In fact, it could have been easier if we just took the trial method here, trial division method. But sometimes combination of both of these is better than just trial method or just by Fermat's factorization method. So the third one I'm going to discuss is about Pollard P minus 1 method. So in this case, we are only going to restrict to a special case. So n equals to pq. So the idea is factorize n equals to pq, where p and q are primes. P and q are primes. You may say, well, this is already a special case, but well, okay, our RSA is also, if we can learn how to if we can learn how to factorize a number n, which is product of two primes efficiently, then we already have a go at Firma at RSA, right? So note the following. So what is Fermat's theorem? So if you look at Fermat's theorem, so Fermat's little theorem, from Fermat's little theorem, we get a to the power p minus 1 is congruent to 1 mod p, right? Where a and p are relatively prime, right? So now suppose if p minus 1 is a factor of L, all right, then we get what this implies. L equals to p minus 1 times k. And then in that case, we'll get a to the power L is congruent to a to the power p minus 1, the whole power k, which is going to be 1 mod p. Now, this means p divides a to the power L minus 1. And now, since p is a factor of n, p is a factor of n, and also p divides a L minus 1. So therefore, GCD of a to the L minus 1 and n, so GCD, this implies GCD of a to the L minus 1 and n contains p, right, includes p as a factor. Then the question is, how to find this L? Right? I mean, like, because if we could find this L, we have L minus 1 and n, we will contain the factor of p. All right. So what does Pollard's p minus 1 algorithm. So to factor n, choose, so step 1, factor n, choose a such that a and n are co-prime. Then you want to get a to the L minus 1. So instead of doing that, what we'll do is evaluate a to the power k factorial for k equals to 1, 2, 3, up to some practical limit, right? So we compute that. And then what we are going to do is we'll find find GCD of AK factorial minus 1 mod n. So with what? With and n. So find GCD of these two guys. GCD of this and GCD of n. All right. So then we will have, and then we can get any non-trivial GCD. So then we get the following: any non-trivial GCD is a factor of n. All right. So for example, let's do the following problem. So problem example. So suppose the problem is factorize 143, which is your n, using Pollard's P-1 algorithm. So here, well, I've chosen n in a way that you can see that the factor is 11 times 13. We have already seen that, but we want it to come out of the Pollard P-1. So here, what shall we take as A? Well, you can choose whatever A you want, really. I will basically go with A equals to 2 because I can right away say that since the number is not odd, sorry, if the number is odd, it's not going to be, it is relatively co-prime to that prime factor P, which we want to find out. So let's see. So 2 to the power 2 factorial is basically congruent to 4 mod 143. Now 2 to the power 3 factorial. Now note that you can do this in a slightly smarter way. This is going to be power 3. So you can use the previous computation here, right? So it's going to be 4 to the power 3 mod 143. What is 4 to the power 3? 4 4s are 16. 16, so 64 mod 143. Now 2 to the power 4 factorial is going to be 2 to the power, so we get 2 to the power 2 factorial, so we get 2 to the power, so 64 to the power what? 64 to the power 4 mod 143. So this turns out to be 27 mod 143. Now let's look at 2 to the power 5 factorial, which is going to be 27 to the power 5 mod 143. So now let's compute that. 27 to the power 5 mod 143. And we get, voila, we get 1 mod 143. Okay, so what is the upshot of this? So therefore, we'll have, if you look at GCD of this and GCD of 143, this has a factor of 143. So G2 to the power 5 is going to be 793 and 143. If you use the extended Euclidean algorithm, you'll find the GCD to be 13. So which is one of the factors of n. So once you get one factor, you can get the other factor is n divided by, so you can see that the other factor is is 11. So this is how the polar row works, right? So I chose 2 here. You could have chosen other primes as well, uh, or other numbers, not just primes. All you need is that A is relatively coprime to N. All right. Thank you for your attention.